Good morning, everybody, and thanks for joining us today. We are exploring efficient HVAC operations in small commercial or small industrial facilities, with Dragos Pereshiv.
Thank you, Megan. So yes, the focus of today's presentation would be on small industrial facilities. We are going to cover a few topics listed on this slide, review common HVAC systems, talk about ventilation in these type of facilities, and then focus more on what's included in the air quality concerns for industrial buildings, reviewing contaminants, how we deal with these in our facilities, talking about thermal comfort, again, related to ventilation and HVAC systems in industrial facilities. And because we are looking at efficient options for our buildings, we are looking at ways to use the heat that we have in our facilities, reuse that heat. Most of it will come from equipment, instruments, devices we have in our space that we want to protect, so that heat can be reused, and we use the heat coming from the process for conditioning the spaces for our building occupants. So let's get started. We are going to first review general concepts of HVAC systems in industrial facilities, and to better understand what purpose the HVAC systems serve in industrial facilities, we can look at this chart that starting from the results, which are focused on the comfort we want to offer to our occupants, moves on to the distribution systems. This is how we transfer energy in our buildings to achieve those results related to occupants. And then we have the primary equipment where we produce the specific form of energy that we need in our buildings. So as an example for heating, we are looking at maintaining conditions related to temperature and humidity for a space for occupants and equipment in some industrial facilities, by distributing energy from a central system through various distribution systems, ducts for forced air, pipes for hydronic systems, and each of them will come with a number of components. And then if you look at where the primary energy comes from for maintaining comfort in the space, in occupied spaces, we have a number of equipment, boilers, furnaces, pumps, fans that help us in this function. So similarly for cooling, we have the end result that we are looking for, which means we want to maintain temperature and humidity levels that are comfortable for the occupants and equipment, with similar systems as we had for heating. And then lastly, for ventilation, which is related to indoor air quality, that means we need to maintain a certain level of indoor air quality for the occupants by providing fresh air, by moving air in the space, and controlling the quality of the air that we have in the space. And that's done again through forced air systems, through fans and filters, dampers, ducts that will mix the air in the space with fresh air. Very popular in small industrial facilities are HVAC systems designed based on this principle of constant volume with variable temperature supply. In these systems, as presented in this simple diagram on the slide, we transfer air using a supply fan. We supply this air into the space, and to maintain the air balance in this conditioned space here, we have a return air. For indoor air quality, we mix some of the return air with outside air, and we have to exhaust a similar amount of air from the return stream to keep the balance. And then we condition that in this example, we show just a cooling coil, but we can do heating, filtration, humidification, dehumidification, depending on what function we are aiming for building comfort in the space. But the key element here is that we are using a constant volume fan, which means that in order to modulate the amount of service we provide to the space, heating, cooling, humidification, dehumidification, we change the input into that particular air conditioning function. So in this example here, we can modify the position of the valve that controls the amount of cooling the cooling coil will provide to the air that is distributed into the space. And because we design our systems for the worst case scenario, that means that we operate the system at part load for most of the time. In order to increase the efficiency of the system, sometimes we are relying on a number of systems that combine, because systems designed by manufacturer for a specific maximized efficiency at a range of capacities will not work properly at in some operating conditions, like for instance low load or different input parameters, like for example outdoor air temperature. So in those cases, we are using a concept called cascade control systems. So we basically rely on multiple units, and we make sure that we keep in operation those items, items of equipment that can maximize the overall efficiency of the system. So in this case, the example shows a modular system with 8 boilers, part load conditions, shoulder months, we need less heating. We don't need to operate all 8 boilers at very low load factor, which results in an inefficient operation of the boiler, but we can select to operate those boilers that operate at the maximum efficiency point on their performance curve as provided by the manufacturers. So in this case, we maximize the system by matching the load required for the space with the most efficient equipment. This example shows the same type of equipment, 8 boilers, but we can mix different type of equipment, like in this example, mixing a baseboard heating with a natural gas boiler system and a heat pump. And based on the operating conditions, we can decide which system is the primary to operate, because that will give us the overall maximum efficiency for this HVAC option. So let's say for temperatures where we can operate a heat pump more efficiently, that's going to be the primary one. As the temperatures drop, we are starting next the natural gas boiler, and then finally we can have the baseboard heaters to provide supplemental heat. I can end my very high-level presentation of the HVAC systems in small industrial buildings without talking about heat pumps, because heat pumps are a very attractive option nowadays for decarbonization and improving efficiency of our buildings. Heat pumps are based on the vapor compression cycle, and I'll show that in a minute. But in our climate here, we use heat pumps for heating and cooling. The most interesting option we have nowadays is to rely on air source heat pumps because of the performance, the improvements in the performance of the equipment and the cost efficiency for this type of systems. But we've seen ground source heat pumps for the longest time, and we still see them in the proper applications in our buildings. Both of them rely on a source for this heat that we are using in the buildings in the heating season. Air source heat pumps rely on the outside air as a source for this heat. and ground source heat pump rely on earth, groundwater, or maybe both as a source for the heat that we are using to heat our buildings. I mentioned that we are relying on a vapor compression cycle, nothing very complicated here. We've been using this for AC, air conditioning, cooling in our buildings for longest time. The system basically has 4 components, 2 heat exchangers, as shown in this chart here. And I'm going to refer to cooling mode first, because that's how we basically have seen this system operating in our buildings for quite a while. And then we have 2 components that control the flow of refrigerant in this loop. So we have a compressor, and we have expansion valve, a metering device that controls how much refrigerant passes through. So in cooling mode, we basically extract heat from the building, from the conditioned space, and we reject that heat in the outside air. And because we are operating at a lower temperature of the conditioned space, we want to cool the space, and we reject heat in the outside air. We rely on this interesting function of the vapor, the refrigerant state in vapor or liquid to evaporate at higher temperatures and condense at a lower temperature based on different pressures. So the interesting thing is that we can revert the cycle. We can change the role of the 2 heat exchangers. So in most air cooling applications, the evaporator would be indoor. This is where we cool our air, the space air. And then the condensing unit will be outside, where we reject this heat to the outside air. So this is where the refrigerant evaporates, absorbs heat from the air, cools the air, and then it goes outside into the heat exchanger that's in the outside air, and it will reject the heat by condensing in that heat exchanger. So if we reverse the function of the 2 heat exchangers, we can use the same device, the same air conditioning system for heating the space. And that's what the heat pump does by using a reversing valve, which changes the function of the 2 heat exchangers. So now the indoor coil becomes the condensing unit. It's going to reject heat into the air space, air that we want to heat by absorbing that heat in the evaporator. That's now the outdoor coil. So we are now absorbing heat from the outside air, yes, at the lower temperature, and we dump that heat into the house, into the space that we conditioned our facility, our building. And we use the compressor and the metering device to control the flow of refrigerant in this circuit here. Obviously, the heat pump in the winter mode will operate harder. If you think about the temperature difference between the outside and the inside air, because that's what the refrigerant does. It basically transfers heat from the outside air coil to the inside coil, to the indoor coil. The temperature difference is much higher during the winter. Therefore, the heat pump is going to work much harder during the winter, and we see that efficiency being impacted in heating mode. So I mentioned that we are focused on industrial buildings, which means that we are going to pay a specific attention to ventilation. Ventilation is one of the functions provided by the HVAC systems, and it's a requirement in our buildings to maintain indoor air quality. So what we understand by ventilation is the fresh air that we provide to the space to maintain the indoor air quality. We can optimize the system by controlling where we provide the fresh air in order to reduce the source of contamination impact on the space. We design our ventilation systems in such a way that we want to eliminate from the space any contaminant that can impact occupants. So we have an airflow that moves from the supply towards the exhaust to push all those contaminants in this direction. And we improve the indoor air quality for the occupants by reducing the contaminants with the exhaust air. So as we exhaust air in big fresh air, we dilute those contaminants in the space. A good system will avoid any short circuit of the exhaust air being absorbed back into the building. So designing properly the exhaust grill and the intake grill locations in the building is important to avoid this short circuit. So indoor air quality refers to what parameters we are monitoring in the space as well as around the space, around the buildings, in order to maintain conditions that are comfortable and healthy for the building occupants. Indoor air pollution is defined by various contaminants, gases that are eliminated in our buildings by process equipment, by building components, materials in the space, organic or particulate, as well as the effect that is impacting our building occupants, like odors, irritants, toxic substances that are related to the indoor air quality measurements. Examples of pollutants that we see in our buildings: excess moisture, carbon dioxide, monoxide, VOCs, and many of these are control regulated so that we can use measurement devices to see where we are within the acceptable range for the indoor air quality for our buildings. So that takes us to the point where we'd like to have a quick discussion about what would be, and I'm going to switch to a Menti slide that will allow you folks to enter responses here. So what would be factors that can impact a person's acceptable indoor air quality? And as you see on the responses on this slide here, it's not just temperature, humidity. It's more than that. Let me take back the presentation to the slides. So acceptable indoor air quality, it's based on limiting the pollution at the source. This will be the preferred option. If we can, that's the main approach that we have in our spaces. We also isolate sources of pollution in our buildings so that we can deal with them in a smaller area of our buildings. We provide adequate supply and fresh air and filtered fresh air so that we can mix with the return air and reduce the concentration. And all these can be done if we can maintain the equipment in maintain that properly designed equipment in good operating conditions. There are standards that deal with the ventilation systems in our buildings. ASHRAE 62.1 is the standard that addresses minimum allowable ventilation and exhaust rates for our spaces. in some cases, we use proxy measurements for this indoor air quality. For example, a simple measurement of CO2 content in the return air will give us an indirect feedback on the air quality factor in an occupied space in most commercial, institutional buildings, residential buildings, and some industrial buildings as well. CO2 being an indirect factor of occupancy, number of people that we have in the space. There are specific requirements for various industries, and we are not going to go into a specific discussion here, but I encourage you to be aware of any specific requirements for this type of facilities. Health and safety is an important aspect, especially if we want to correlate to energy efficiency. So how we design our HVAC systems to increase the effectiveness of indoor air quality in our facilities. The three examples shown here go from a high mixing of the air in a space, which results in kind of homogeneous distribution of the concentration of contaminants, to the less mixing of the air, and we call this displacement ventilation systems, where we slowly transfer the air in the space so that we can eliminate those contaminants with less mixing of the air, therefore in a more efficient way. So for industrial ventilation systems, we can approach them in four major categories. Industrial air conditioning for comfort of the occupants. We look at general ventilation systems or local ventilation systems if possible, as well as process ventilation systems addressing specific phases of the process. In order to better design an HVAC system in an industrial facility, we need to keep in mind that zoning is very important. In many cases, we have specific areas where we can control the emissions of various contaminants. We define this as a control zone in which thermal comfort as well as air quality need to be maintained within specific ranges. We can have this defined as a large area in the facility. Therefore, we need to control those contaminants throughout the entire main control zone, or we can zone it in such a way that we have local control areas, zones, which will change, will modify depending on the source of contaminant for that particular zone. In uncontrolled zones, those are typical general areas that would not see the same level of contaminants. These zones could be within that main zone, some areas that do not need to maintain or do not see the same level of concentration of contaminants. The capture zones are zones in which the source emission will be captured close to the emitting point. We have local exhaust systems that take care of this, so preventing mixing of these contaminants in larger areas in the building. So keeping the zoning in mind, we can now address the four type of systems we see in industrial facilities. We see the industrial air conditioning systems where as is shown in this example here, we are eliminating exhaust air from the space with contaminants that are capturing this air, and then we provide fresh air to the space to dilute those contaminants. So We do, in this case, address heating, cooling, filtration, see various components of the supply air systems. We also filtrate the air that's exhausted to maintain a certain standard for the exhaust air so that we do not transfer the pollution, all that pollution outside if it's not acceptable. So we have the supply system and the discharge systems that rely on the dilution of the concentration of contaminants in the space by providing this fresh air. Room air conditioning strategies that we see in our buildings, as presented in the slide here, we are controlling parameters for comfort, heating, humidity, and contaminant distributions are a function of our measurements for the space, comfort, and indoor air quality. We have various strategies that we implement in the space, piston type of distribution stratification, relying on the density of the air at various temperatures to transfer this contaminant, zoning by applying a local control, and then mixing, which is basically an uniform condition throughout the providing uniform conditions throughout the entire ventilating space. And based on the typical process analysis, you can look at which option would work better in each case. So in eliminating the contaminant from the space, we select the ideal or the most effective solution. Some of these examples will show eliminating this contaminant by pushing the air along the room, along the space, and exhausting it at one end. We see here we rely on the density of the air to move through the room and being exhausted, or the last one here, the mixing that happens in the entire space, so we dilute the entire space concentration of the contaminant. For local exhaust ventilation systems, we've seen this in many industrial facilities. We design a control system, a capture system that is localized where the source of the contaminant happens, and then we exhaust this air before preventing this air from mixing in a larger building space. The typical structure or schematic for local exhaust system is shown here. So we have the hoods that will capture the air close to the source. We transfer that into duct systems. Many cases include some cleaning devices, and then after we clean this air, we exhaust this air into the outside so that we can bring fresh air and maintain the indoor air quality in the space. So we have an exhaust stack that will distribute this air outside and mixing with the outside air to reduce that concentration of the pollutants. Gas cleaning systems that we see in our system, in our buildings as well, in industrial facilities, are designed specifically for the contaminant that we want to eliminate. Dynamic separators, fabric filters, wet separators, electrostatic precipitators, SOx control, NOx control, all these are type of treatment for the exhaust so that we can reduce the amount of pollutants we release in the environment. But we reduce the amount of contaminant in the space by exhausting this outside. Designing industrial ventilation systems. We talked about the mixing ventilation, which reduces the concentration of contaminant by dilution. We provide this air in the space. We mix clean, fresh air with the room air, and we reduce that concentration. Displacement ventilation relies on higher density air that moves, pushes the air in the space into one direction, and then we reduce the mixing by directing the contaminant towards the exhaust from the space. See an example of one of these systems that we have in our industrial facilities. We rely on the flow of the air that entrains some of the secondary air from the space to exhaust the mixed air with a contaminant into the exhaust systems. Demand control ventilation is a concept applied in our HVAC system design, because most systems will be designed for the worst case scenario, but we most of the time apply a modulating strategy to operate the system at the required capacity for our space. So it's an energy saving strategy because we control the flow of air, fresh air or recirculating air based on occupancy and the indoor pollutant load. Once again, designing the systems for a worst case scenario means that we have various conditions in the space that will allow us to achieve savings by reducing the capacity of our ventilation system. So we monitor the concentration of these contaminants so that we can adjust the output of our ventilation system to keep the contaminant within the acceptable range. This is allowing us for low activity level or low occupancy level to achieve savings. The demand control ventilations can save a tremendous amount of energy because the function of power versus airflow, for example, is not a linear function. So, for example, in a system where we can reduce the airflow by 50%, the power required by the ventilation system can be in a cubic relationship reduced by 8 times. So we talked about indoor air quality that's controlling pollutants, contaminants. Let's see what do you mean by these contaminants. So I'll get to the second poll question. And that's basically related to what type of exposure we have for occupants in our buildings to various chemicals and pollutants. And you can see on the slide here in the answers how we can get exposed to various sources. Now, if I'm to summarize this, basically, we define all those pollutants as any unwanted liquid, solid, or gas in our buildings that results from the activity in that space. So we have primary and secondary pollutants. Primary pollutants are discharged into the ambient air that we have in our facilities. And secondary pollutants will result from reactions that happen in our buildings based on the primary pollutants. Contaminants are basically all those pollutants that impact the indoor conditions, the indoor air quality conditions. We have various gases or chemicals identified here: carbon monoxide, ammonia, chlorine, hydrochloric acid, sulfuric acid. So there are various chemicals that are present in our spaces. Quite often accidents happen based on these pollutants that are not well controlled in the space. So in order to provide the indoor air quality expected by our building occupants, we basically have various regulations. I think we are all familiar with the Workplace Hazardous Materials Information System that is in place in Canada. This system requires a clear identification of various substances that can impact the health and safety of building occupants. It's a system that classifies hazards and shows specific information about this system, about these substances on safety data sheets. There are requirements in terms of awareness and education for occupants that are maintaining the legislation. And all this is in place to reduce the eventuality of those accidents related to substances that can impact our buildings. There are three main ways we can see these pollutants, these chemicals impacting our occupants: inhaling, absorption through the skin or eye, and ingesting. And the results, the negative results that we see on for these substances are acute harm, chronic harm, nuisance, and corrosive actions that can impact our buildings. And occupants.
Are we still viewing the Menti slide?
Oh, sorry.
No worries.
I forgot to share, so I'll have to return.
Great.
So talking about contaminants, we see various substances, various chemicals. Very often accidents are related to one of these five listed here: carbon monoxide, ammonia, chlorine, hydrochloric acid, or sulfuric acid, as a result of many of the industrial processes in our buildings. So what we basically want is to have in place systems that can address how any type of liquid, solid, or gas product can impact our buildings. These would be results of activity in our facilities. We have primary and secondary pollutants. Primary pollutants are directly released in the space from the process, and then secondary pollutants would result based on a reaction of the primary pollutant that happens in the space. So in our buildings, we address the health and safety for our facilities based on various regulations. The Workplace Hazardous Materials Information Systems, WHMIS, is the standard we apply in Canada. The elements included in this standard are hazard classification, labeling with relevant information, all these substances. We have safety data sheets with the information that can assist building occupants in better understanding the impact of these substances. And we have an awareness and education program for building occupants as part of the standard. There are three ways that our building occupants can be impacted by various substances. Inhaling, absorption through the skin or eye, for example, as well as ingestion are these examples. And the effect, the harm produced could be classified as acute or chronic, or just a simple nuisance, or corrosive impact of the substance. So when we design our HVAC systems to improve the indoor air quality, we focus on identifying the contaminant sources. We find mechanisms to transport this contaminant in ventilated spaces. And then we design the system so that we force the air introduced into the space to direct the sources of contamination towards the exhaust. We use free convection flows that can carry the contaminants towards the exhaust. We typically design, or we try to design airflow near the source of the pollution. We will have general exhaust for the rest of the space. We rely on air transfer properties, the aerodynamic means for larger opening protection. Airflow through the openings and cracks of the building is accounted for. We have this secondary effect of fresh air coming into the building through these opening and cracks of in the building envelope. So when we classify our contaminant sources, we are looking at internal and external sources, as well as our HVAC systems to be one source of contaminant pollution as well. Better understanding the system will allow us to design the indoor air quality maintaining system in a proper and effective way. So let's talk about external sources first. Yes, we assume that the outdoor air is generally less concentrated in these substances, pollutants, than the return air, but we need to be sure of this. Many cases, if you are in a very high traffic area, or let's say the design of the HVAC system placed the intake of the fresh air near a loading dock, you may actually see issues with the fresh air to be more polluted than the actual air in the space. But in general, we assume that outdoor air is less polluted than the air in the space that we want to dilute. So we use outdoor air for dilution. We definitely want to avoid the short circuit, the exhaust being recaptured back into building. Outdoor air contamination problems can be in industrial areas based on exhaust from some of the processes, power plants, motor vehicle exhaust, dust, asphalt vapors. Many sources of pollutants can come from outside, and we need to be aware of them as well. We also look at the impact on the comfort conditions of the space through various heat transfer options we have through the building envelope, both conduction as well as radiation or even infiltration to those cracks and openings of the system. So the HVAC system could even further enhance those sources of pollution from the exterior. The HVAC system not maintained properly can be a source of pollutants. We hear, I wouldn't say frequently, but once in a while we hear about cracked heat exchangers in rooftop units that release flue gas into the space and poisoning the building occupants with combustion products. The worst case scenario here would be an incomplete combustion that releases carbon monoxide into the space, into a conditioned space. Microorganisms are present in humid areas of the HVAC system, like cooling coils, humidifiers, filters. That's another source of concern for HVAC systems. And all this typically is related to some form of incomplete maintenance or improper maintenance for our HVAC systems. And finally, we get to the internal sources. These are especially important in industrial facilities because we have more process equipment in our facilities. In that case, we have air contaminants coming from processes that can include release of dust, fumes, fibers, other gases. Some of them can mix into the space, like, for example, heat coming from the equipment. We have biological hazards that can be present in these processes. Just think about healthcare facilities. We have physical hazards as well, thermal parameters, temperature, relative humidity, or air velocity impact the comfort of the occupants in the space as well. But beyond that, we have electromagnetic fields, noise, vibration, illumination. Like, there are various parameters, physical hazards that we identify in our facilities, and we have to address them in order to maintain the indoor air quality and the indoor environment quality that we need to provide for building occupants. So identifying the contaminant sources will include installation of sensors, so we can measure the concentration locally. We need to see when, how, where we have these contaminants released in the space. We have directly reversing transport equations to track the source based on the measurements we take. We have solving forward transport equations to match a source to some of these measurements. So we monitor the concentration at a sensor. We monitor the concentration of a certain pollutant at a sensor, and we match this with a source so that we can identify this relationship. So in a mixed air distribution system, the primary air that we supply to the space will engage some secondary air in mixing the air in the space and diluting the concentration. This is for spaces where we have a single loop. Small spaces will have this single loop of fresh air distributed in the space. Larger areas can result in secondary or even tertiary loops for the air that's distributed in the space, and therefore mixing supply air with existing air in the space. And transfer from one loop to another will be happening at the contact points the space. Now, a better way to control the concentration distribution would be using displacement ventilation. In this case, we try to actually avoid or reduce the mixing so that we can direct the contaminant, in this case, heat or another contaminant source, to direct this to the space where we use for exhausting the air. So supply will be directing this contaminant towards the upper side of this room here, and therefore allowing us to exhaust the higher concentration of the contaminant from the space. Unidirectional airflow, it's a similar intent, is to control the airflow in one direction and then try to eliminate the higher concentration pollutant from the space so that we can provide this exhaust function here at a lower volume for the space. We can increase the concentration in various ways. So this example here shows a spiral vortex air distribution. So basically supply air is provided to the space in such a way that the concentration of contaminants will be increased into the center of this area and then exhausted from here. I mentioned that thermal comfort is related to indoor air quality. I mean, when you talk about thermal, temperature comes to mind, but it's more than just temperature. So I'll go back to the Menti slide here to see what factors impact our occupant thermal comfort. And as I said, it's not just temperature, and the slide here shows some of these identified factors: humidity, air velocity, and in a dynamic system, even the degree of temperature change on a certain specific interval of time impacts the perception of comfort. So returning to my slides,
Oh, you're muted.
So thermal comfort is a subjective topic related to the perception of space occupants. It's expressed as satisfaction with the thermal environment, and as I said, we may have two different occupants with two different perceptions of the space, of the same space conditions. But what we are focusing on is to understand where the thermal discomfort comes from and what impact it has on our bodies. So thermal regulation is a function that we rely on maintaining our body's comfort, and that basically changes based on productivity output, can cause accidents, mistakes. So we need to be maintaining this thermal comfort because of the implications that we have in our facilities. There are both primary factors and secondary factors that can affect how we perceive thermal comfort. And there's a lot of research done. We use in defining thermal comfort and acceptable conditions for thermal comfort, we use the ASHA standard 55. There are other standards out there, ISO standards, for example, that define thermal environment for our buildings. The primary factors that are related to the thermal comfort are the body temperature, the metabolism of our bodies, and physiological temperature regulation, how our bodies maintain the temperature. You can see here in the diagram showing that we have various functions related to the level of activity, how we control our heat, our temperature, and we rely on convection, radiation, conduction, but as well as evaporative effect of our sweat to maintain the temperature of our bodies. So that's how we can survive in environments where the temperature of the space is even higher than our body temperature by relying on the evaporative cooling effect that happens when our bodies sweat. Secondary effects are impacting the perception of the comfort based on other factors like age, gender, maybe just a subjective perception of the thermal satisfaction. Typically, we see older people maybe being more sensitive to changes in the temperature than the young people, female more impacted by these changes than males. Other secondary factors are impacting perception of the building occupant, like circadian rhythm, changing time zone, or working in shifts can have an impact. Physical disabilities, fitness, ambience of the environment, color, local climate. There are various secondary factors that can impact our perception of comfort. In Action Standard 55, we identify clothing as being one element that has a significant impact on thermal comfort. By using layers, we can impact the flow of heat and moisture between our body and the environment, and that impacts the perception of the thermal comfort. So we're again relying on convection, conduction, radiation, as well as the moisture transportation for maintaining our temperature. So the more layers we have, we basically increase the R value, the insulation, so we have less heat that we can release. Indoor humidity, that's another element that defines thermal comfort. And when we refer to indoor humidity, we are working with a relative humidity. This is in our buildings, in most of our buildings, a range of 30 to 60% to associate with perception of thermal comfort. This is based on, I guess, various type of buildings, various type of activity. We have a range that we try to maintain. Time of the year, time of activity level, all those will have an impact on relative humidity target or set point for the space as well. What happens if we have low relative humidity in the space? Negative impacts, dry nose, throat, eyes, because of the increased evaporation of moisture from our body. We may see also in dusty environments that function of perception of low comfort in dry environments being increased. So we try to maintain a minimum of 30% relative humidity in the spaces. Now, on the other range, at the other end of this range, beyond 60%, we start to see the perception of comfort to be reduced as well, especially in warm zone when we combine the thermal effect, the temperature effect, with a higher relative humidity as well, to create a discomfort perception for being occupant. So we try to maintain relative humidity below 60%. And it just also so happens that within this range, 30 to 60%, we have an optimum for other microorganisms in the environment as well. Air velocity is a parameter that we try to keep for perception of comfort. I mentioned that higher velocity creates a perception of draft. So for areas where activity levels are low, like let's say a library or an office, we may want to have a low velocity of the air, less than 50 feet per minute would be not even noticed. Somewhere between 50 and 100 feet per minute would have a pleasant draft feeling for the occupants. As we move in higher velocity ranges, we'll see the perception of comfort reducing, and typically we associate this with areas where we have a much higher level of activity present. Heat stroke is a concern that we need to keep in mind for industrial facilities. In many areas, the heat generated by the industrial processes can have an impact on the occupants. So we basically identify the heat stroke with a reduced function of our body's cooling system. So we cannot maintain the body temperature with a typical heat transfer options. We have convection, conduction, radiation, and evaporation. So now, by accumulating heat, the temperature increases to a point where we can create irreversible damage to body organs. Some people lose the ability to sweat, and that's really an important component of the temperature control mechanism of our bodies. If you rely only on convection, conduction, and radiation, you reduce the ability of the body to reject heat by not having that evaporative cooling effect. The type of systems present, aside from the noticing of the body temperature increase, and as the body is not able to reject that heat, the temperature will increase. We have fast pulse, headaches, weakness, maybe passing out can be present. So all these are important symptoms that identify heat stroke. So therefore, we need to prevent, and if need be, treat heat stroke event for our building occupants. But before we get to the treatment, what we want is to reduce the activity level to a point where the bodies can now maintain the temperature by rejecting the amount of heat required, reducing the heat exposure. Again, by eliminating that source, we can prevent the heat stroke. Having enough fluids intake that will prevent us from reducing the evaporative cooling, the sweating that can happen. And definitely look at the symptoms I mentioned before to identify them early before they become irreversible. In terms of treatment, basically specialized healthcare staff will be involved. We provide cooling, drink fluids, reduce that R value of our heat rejection from the bodies by removing excess clothing. So these are methods to treat, but again, once again, we would better address this early on in the prevention phase before treatment is required. Heat has also a negative impact on equipment and instruments. We look at heat as a byproduct from our systems. We know that all energy eventually transforms into heat from electrical systems through resistive effect will convert into heat. Lighting systems generate heat as well. So we just need to understand where this is generating our equipment and how that impacts the performance of the equipment we have in our facilities. So we need to design the systems in such a way that we can reject that heat properly, maintaining the parameters for the equipment, because otherwise the performance of the equipment drops quite significantly. And this chart here shows an example of the performance we expect from a device in our building that operates at higher temperatures over the time. So if we operate at a lower temperature, let's say 40 degrees, we expect a 10-year lifetime of this equipment. But if we operate now the system in higher temperatures, we can see significant reduction of the lifetime of this equipment. So at 70 degrees Celsius operation, we can see now we have just over 1 year of lifetime for the equipment. So significant reduction in the lifetime of the equipment at operating at higher temperature. Examples here of what would be the recommended temperature range by manufacturers. VFDs, very popular devices in our buildings here, where we try to modulate the output of the fans or pumps. Typically, they are designed to operate properly for temperatures up to 40 degrees Celsius. If we can reject the heat more efficiently by having external heat sinks, we can increase that temperature to 50 degrees Celsius. Some of the other devices that you can see listed on the slide here. In many cases, we see now equipment being designed to operate at higher temperatures because we see that as being a way to improve efficiency. For example, servers are designed to operate at higher temperature so that we can improve the efficiency of the data center. We are looking at 40 degrees Celsius, and if we have cooling fans, the server temperature can actually operate at 55 degrees Celsius. So it's a quite significant amount of heat that is generated by these devices here. As I mentioned, pretty much all this energy, or a significant component of the energy, converts into heat. So for electrical components, where we see the conversion of electricity into heat, what we have impacts on our systems. The higher the power, the electric power, the higher this effect of heat released from the equipment happens as well. So higher heat release impacts the performance of electronics. microprocessors, pretty much all solid state components that we see now in our equipment. So pretty much all the energy absorbed is converted into heat, and that's what we need to eliminate from the space, from the equipment into the space. Now, removing this heat is based on various heat transfer principles. We use natural convection. As the heat is released, we see the heat being transferred from the high potential, high temperature to a low temperature. So we extract this heat from the equipment, from the electronics to a heatsink, and then that heatsink releases the heat into the space. Warm air will rise and then allow for cooler air to come into the heat exchanger and then extract more heat. We can use forced air flows, blowers, fans, that can actually increase the heat transfer function. We see air-to-air heat exchangers so that we can have a closed loop for the cooling. We see water-to-air heat exchangers, water being a media that can transfer more efficient the heat than air. Or we can even see air conditioners that will use the vapor compression cycle I described early on in the presentation to remove this heat from the source and transfer it outside. So for system design and economic considerations related to these systems, we try to avoid condensation and dust accumulation. We use NEMA standard for enclosure ratings, and we look at what would be the economic impact of designing this cooling effect, these cooling systems. So releasing the heat from our equipment. But this heat that we have in our buildings can also help us. So to improve the efficiency of the HVAC systems in industrial facilities, we are looking at controlling the heat transfer, heat flows in the space, and recovering and reusing the heat whenever possible. For controlling, we use temperature controls, thermostats. This will allow us to modulate the HVAC equipment output to maintain a certain temperature in the space, either heating or cooling. We use timers or movement detectors, space occupancy detectors. We use differential pressure sensors that will trigger change in the filters, for example, or be able to identify early on maintenance requirements, predictive maintenance requirements, for instance, a coil that's plugged with dust. We use light sensors to control the output of our lighting systems, photocells that can turn fixtures based on the outside light level, occupancy sensors based on occupancy. Ventilation on demand is one of the strategies we apply in our systems for improving the efficiency of HVAC systems in our buildings. Designing systems is based on the principle of being able to provide the service at worst case scenario type of conditions, and ventilation on demand is a way to achieve savings when the system is not at full capacity, it's not required to operate at full capacity. So basically, having sensors that will monitor the conditions of the space will allow us to reduce the ventilation in a garage, for example, when we have lower level of activity in space. Ventilation on demand systems, modern control systems are based on standard sequences of operation that learn how the space responds, how quickly our HVAC system can return the conditions to the acceptable parameters. So we are implementing them to optimize and improve the efficiency, increase the efficiency of the systems operating at variable conditions. So using these sensors will not only allow us to improve the efficiency at part load type of operating conditions, but are also meant to identify early on problems that impact the indoor air quality, the indoor environmental quality, and trigger response, an early response that will reduce the impact on the building. We use alternative methods as well to improve the efficiency of our buildings, like for example, infrared heaters. Instead of heating the entire volume of the air in the space, we direct this heat to the surfaces. This is efficient in cases where the activity level requires, for example, frequent openings of overhead doors, like garages. Adapting the layers of clothing, it's also an alternative method. Having various spaces in the facility with specific clothing provided to workers. That's an activity that's related to the activity level. Destratification fans. We know that in high ceiling areas, warm air will rise and will create a differential temperature across the height of the space. So using destratification fans properly can increase the mixing and controlling destratification to an effective operation of the space. Adiabatic cooling, that's another method of improving the efficiency. So basically, we are using a closed ambient circuit for the air, and we use water for the evaporative cooling effect only if required. So in this last slide of the section here, we are going to talk about heat recovery, because we can use this heat that's generated by various processes in our buildings to improve the efficiency of the HVAC system. So typically, we have exhaust air from the space that's conditioned. So it has heating during the heating season, it has cooling during the cooling season, and we can reuse that heat to reduce the amount of conditioning required for the fresh air. So we do that by using heat exchangers. We have heat recovery ventilators. The difference between heat recovery ventilators and energy recovery ventilators in the industry is just what type of heat we are recovering. So for heat recovery ventilation, we are focusing on a sensible heat. And for energy recovery ventilators, we focus both on sensible and latent heat. So basically, we recover the moisture from the exhaust there as well. So the effectiveness of these heat recovery systems in today's level of performance for the equipment is ranging somewhere between 75% and 95%. So a significant amount of energy that we can recover. So how that works, basically, you have the two streams. One would be the fresh air that's provided to the space, and then is the exhaust as a second stream that's extracted from the room and then exhaust into the outside air. And as I said, the extract air from the space is conditioned. It has cooling during the summer and it has heating during the winter that we can reuse. And that heat is transferred to the fresh air in this heat exchanger. The type of heat exchanger will define if we have a heat recovery ventilator or an energy recovery ventilator. The difference, as I mentioned, being the latent heat. And that takes us to the last poll of our presentation here. So let me share it. So what we are looking for, is there a specific consideration that will impact the heat recovery in small industrial facilities? And I'll return to my presentation here to do a quick review of where these opportunities are. So in facilities where we have boilers, we have a significant opportunity for heat recovery from the flue gas. Boilers eliminate from the combustion flue gases, and these flue gases passing through the boiler stack are exhausted in the atmosphere, in the external, in the outdoor air space with a significant amount of heat, especially for those ones that will have vapors from the combustion reaction present into the flue gas, so without condensing that. So the most often seen type of processes, industrial processes in our space that generate heat, aside from the boilers, are exothermic processes, releasing heat based on a chemical reaction, thermal oxidizers, and the equipment themselves. So compressors, pumps, fans, hydraulic equipment, engines, they all have a heat rejection that can be reused for our space needs in heating mode. So if we look at additional considerations for heat recovery, we have, yes, heat recovery is an important element that we focus on, but we have to be aware of that extract air, the exhaust air that carries with the heat, may also contain a higher level of contaminants. So this extract air may contain corrosive substances, chemicals that can dissolve in water. So we have to be designing the heat recovery system in such a way that the impact of these contaminants do not affect the performance of the heat recovery system. So heat recovery units may change the indoor moisture level if the condensation happens. We're talking about the ERVs, the energy recovery unit, because they have both latent and sensible. But with that water condensing, we can also deal with icing or frosting that can happen on a heat recovery unit. So in colder climates, the exhaust air moisture can be condensing if we reach a dew point, or even further freezing if we reach the freezing point on the path of removing heat from the exhaust air to transfer it to the supplier, to the fresh air. So in equipment manufacturing world, we have various technologies that are trying to improve the efficiency. We are looking at membrane energy exchangers that allow improving the efficiency of this heat transfer, both latent and sensible. We are looking at runaround heat exchangers. Heat pipe based heat exchanger system is also a concept that will allow us to remove more heat from the exhaust and transfer it to the incoming airflow, or using actually heat pumps to further remove more heat from the exhaust air and transfer it to the incoming fresh air. That basically concludes our presentation. So we'll open the floor for questions, and maybe a brief description of other features that are available for all participants in these type of webinars.
Thanks, Dragos. This was a very informative session today. We do have an offer on for any participants of the Save on Energy training and support sessions, post-webinar support. So we have an intake form which will be available on the shared copy of these slides. And coaching sessions are typically conducted virtually, but you can access a coach one-on-one, and depending on the nature of your request, we try to align you with the right coach for the type of help that you're looking for. And then lastly, we have some information about how to access Save on Energy programming, how to contact us at training and support, or how to sign up with this QR code for Save on Energy's quarterly business newsletter. Thanks once again, and have a great day.
Thank you, everyone.